So hello, in this video we'll be talking all about torsion. So simply, torsion is the twisting of an object. So if this is your object, for example, it due to the action of torque or rotational movement, or simply just a moment of a force, so it will create a rotational or twisting effect on your object because of these forces, no? Torque is just a rotational equivalent of your linear force. So torsional shearing stress, because of the twisting motion, it can create a shearing stress, which is in this case we call it the torsional shearing stress, because then again it is caused by your torque or moment created by your force, which is on distance d. So the equation for solving the torsional shearing stress is this one. We also have the symbol for shear, tau, equals torque times rho over J. And then rho here is the distance from the center of the shaft to any point of your circular area. And then the stress max is at the outermost point, which is now represented by your radius. J here is the polar moment of inertia, or this is the resistance to torque or torsion. So this is the resistance of the shaft, torsion, that's why it's in the denominator, because the bigger your J, the bigger your resistance to torsion, therefore it decreases your torsional shearing stress. So for cylindrical solid rods or shafts, we have here J is just pi over 32 d to the fourth, no? So the unit for J is actually L over L to the fourth, no? Or mm4. Usually it's in SI, we have the unit for this is mm4 for SI unit, and equivalent we have inches for the English units. So using if you have this one, J equals pi over 32 d to the 4, and when you substitute this to here, knowing that R is just d over 2, you will arrive at this equation of the stress max for solid cylindrical. So, but if you forget this one, just know that stress max is equal to torque radius over J. Of course, you know that radius is just equal to d over 2. Then you just have to substitute that here. Then this will become d over 2. Then you have the J, which is pi over 32 d4. By the way, you can find this equation in some books, especially on mechanics or statics of rigid bodies, your moment of inertia, polar moment of inertia. So you have a table for this for all shapes, so you can refer this to your statics of rigid bodies books or mechanics books, and you just browse through the tabulated equations for different shapes. So for this one, this is for circle. So cancel 3, this will be cancelled, this becomes 16, and then of course it becomes 16t divided by d3 pi. So just in case you will forget this one, because of too many memorizing too many questions, it's important that you know where this come from. For hollow cylindrical, meaning we have a hollow part, so you have outer and inner diameter. You have the inner diameter d, and then you have the outer diameter d. So that's why it's you have two diameters here. This is the outer, this is the inner. So this is the equation. Again, the process is still the same, but now you have two diameters. And so you just have to remember these equations. For angle of twist, you can observe in this drawing, if there's an introduction of torque or action of torque, your this line L actually will be twisted, and then it will create this angle, and we call this angle of twist. It's just represented by your torque times L divided by JG. And then we're familiar with this letters. This is the torque, this is the length L, presented in this drawing, and then you have the J, which is the polar moment of inertia, and then you have the modulus of rigidity or the modulus of elasticity in terms of shear. And then you also have the power transmitted by a shaft. So you have P in power equals torque times your angular velocity, and angular velocity is also equals 2 pi f, no? Excuse me, where f is your number of revolutions per second. So that's how you get your power due to your torque, no? So if you're familiar with shafts, sometimes it's one way of transmitting your power, no? So especially in mechanical engineering applications, they're used to these types of concept. So that's it for the introduction to torsional shearing stress or torsion. So we'll have sample problems and separate videos. The link will be posted in the description of this video, so you just refer to those links for sample problems.